Greetings, my dear friends. Welcome to the official channel, The Midnight Lecture. This is the place where dreams become knowledge, and that very voice guides you through the silence of the night. Tonight, we will lift our eyes to the sky, to where, for billions of years, a star named the Sun has been pulsing, where one after another the planets waltz in their eternal dance, where emptiness turns out not to be empty at all, but a majestic canvas upon which time is painted by galaxies, meteors, and auroras. Close your eyes. Imagine you are floating weightlessly through space, like a drop of light. Around you there is cold and silence, but somewhere in the distance our home star, the Sun, is shining. We will set off on a journey through the solar system, look into its heart, see fiery Venus, study Earth and the Moon. We will fly over the storms of Jupiter and the rings of Saturn. We will reach the icy outskirts and touch mysterious comets. Before we begin, let me remind you, if you enjoy these slow nighttime journeys through the worlds of the past and future, don't forget to subscribe, because by the end of this lecture, you will be fast asleep. This will help our channel shine brighter, like a new star in the night sky, and you will always know where to return when you long for peace and meaning. Now wrap yourself in a blanket, close your eyes, let go of the worries of the passing day, and let my voice guide you through the silence of the night, far away, to the stars, and to the very essence of things. We begin. The solar system is an island of life in the middle of the icy ocean of space. It seems tiny on the scale of the universe, but if we imagine it scaled down so that the Sun is the size of a football, the Earth would be the size of a pinhead, orbiting at a distance of 25 meters. And even at that scale, the distance to the nearest star would be more than 7,000 kilometers. But let's start from the very beginning. The birth of the solar system. It is about 4.6 billion years old. If we imagine this time as a single day, then humans appeared only in the last 2 minutes before midnight. We are infants by the standards of the stellar family. The system arose from a giant cloud of gas and dust, like a mist the size of trillions of kilometers. At some point, the equilibrium of this cloud was disturbed, perhaps by the explosion of a nearby supernova. A wave of energy passed through the cloud, and under the influence of gravity, it began to contract and rotate. In the center, the Sun flared up, dense, hot, a flaming core of hydrogen and helium. Around it remained a rotating disk of dust, like a thin, flat pancake. From its particles, very slowly, the planets, comets, and moons were born. It was a natural process, but with an astonishingly harmonious result. The orbits stabilized, the planets spread out by distance. Some kept their gases, others became solid bodies. An architecture emerged that we are still studying today. What does the very word system tell us? It is not just a collection of bodies flying in emptiness. It is a built, gravitationally bound structure. The Sun in the center is like a conductor. The planets are the orchestra. Each plays its own line in a great cosmic symphony. The orbits are precise, stable. The system lives in rhythm, slowly revolving around the center of our galaxy. The inner bodies, closer to the light, are rocky, dense, and warmed. The outer ones are icy, gravitationally powerful, far beyond the boundary of solar warmth. Between them are asteroids, satellites, comets, and invisible interplanetary dust that we do not notice. But without it, the whole mechanism would be different. Today, all the planets of the solar system can be conditionally divided into two worlds, inner and outer. This is not just about location. It's two different types of planets in composition, structure, and formation. The inner planets are those closer to the Sun: Mercury, Venus, Earth, and Mars. They are called terrestrial or rocky planets. They are relatively small, dense, with solid surfaces. Their atmospheres are thin or completely absent. Why? Because when they formed, they ended up too close to the Sun, and its heat simply did not allow them to retain light gases. They are like burnt stones by the campfire, scorched, solid, weathered. Beyond them, far past the asteroid belt, begin the outer planets: Jupiter, Saturn, Uranus, and Neptune. They are called gas and ice giants. They are much more massive than terrestrial planets, but consist mostly not of rock, but of gases: hydrogen, helium, methane. They have no solid surface, only dense clouds and perhaps hidden cores. Their atmospheres are deep and boiling. Their rings are complex and varied. Their moons are separate worlds. Let us imagine our galaxy to understand our cosmic address: a huge rotating disk with curved arms like a giant seashell sprinkled with stars. This is the Milky Way. It contains up to 400 billion stars. Our solar system is neither in the center nor at the edge, but in one of its arms, the Orion arm. It is like living in a residential district of a huge metropolis. Not too noisy, not too crowded. An ideal place to live. We are about 27,000 light-years from the galactic center, and together with the whole system, fly in orbit around the galactic core at a speed of about 800,000 kilometers per hour. One such orbit takes about 230 million years. That means everything you know, human history, the dinosaurs, the formation of Earth, all happened in less than 1/10 of a single galactic revolution. We are newcomers in this motion, and yet something makes our solar system, and our planet Earth in particular, special. The solar system is remarkably stable. The planets do not collide. Their orbits are almost circular. The Sun, a star of average mass, not too hot, not too bright, but stable. It does not explode, does not fade, does not tremble. On the third orbit from it lies Earth. And here everything came together to give rise to oceans, an atmosphere, breath, and mind. And then there is the Moon, our constant companion. Jupiter, the giant that deflects dangerous bodies, and the magnetic field that shields us from the solar wind. You can call this a coincidence or the design of nature. But the fact remains, here, in this system, a being appeared capable of looking back and asking the question, where do we come from? When humans first looked at the sky, they did not see the solar system. They saw only the mysterious pattern of stars and a few slow-moving lights. The planets. Everything seemed to revolve around them. And indeed, at first glance, Earth is motionless, while the sun rises and sets. The moon grows and wanes. It was a natural illusion. Thus was born the geocentric model of the world, with a stationary Earth at the center and heavenly spheres around it. It was not just a theory, but a complete worldview. The cosmos is a layered pie, where planets move in circles inscribed in ideal heavenly orbits. This was the science of the ancient world. This model was perfected by Claudius Ptolemy in the 2nd century AD, and it lasted for more than 1,300 years. But in the 10th century, everything changed. Nicholas Copernicus, a Polish canon and astronomer, put forward a simple yet revolutionary idea. The sun is at the center, and the Earth is just one of the planets. This explained observations much more simply and elegantly, but it was daring. The world was not ready yet, and still, science moved forward. the 10th century, Galileo Galilei built a telescope and pointed it at the sky. He saw that Jupiter has its own moons, which meant not everything revolves around Earth. He saw that Venus has phases, like the moon, which is possible only if it orbits the sun. He saw that the surface of the moon is uneven, with craters and mountains, meaning heavenly bodies are not perfect, as previously believed. These discoveries shook the world. Galileo was accused of heresy. He was forced to renounce his views, but the phrase attributed to him after the trial remained through the ages. And yet it moves. Then came Johannes Kepler. He proved that the orbits of planets are not circles, but ellipses, with the sun at one focus. Then Isaac Newton explained why planets do not fall into the sun and do not fly away into space. Gravity and inertia create a stable orbit, an eternal balance between falling and motion. Step by step, humanity moved closer to the truth. We began building observatories, recording planetary positions, searching for patterns. We discovered Uranus and Neptune, and in the 19th century we realized that the sun is a star, and the stars are other suns. In the 20th century, a new era began, the era of spaceflight. We started not only looking at planets, but flying to them. Satellites sent back images of the far side of the moon. The Voyagers showed us Jupiter, Saturn, and their moons. The James Webb Telescope now looks beyond the solar system. We now know. The solar system is not the center of the universe, but it is our center, the center of our observation, our understanding of life. The solar system is not just an object in a textbook. It is a living, breathing, cosmic organism in which everything is connected, with the sun at its center, a huge star holding everything around it. The pulse of our system, the heart that radiates life. The sun. When we say this word, it feels like we know it. We see it every day outside the window, on the horizon, reflected in the water. But that is only an image, just light that has broken through the atmosphere. The sun itself is not a circle in the sky. It is a star, enormous, ancient, constantly burning. It is unlike anything we encounter on Earth. It is a fiery sphere of plasma, heated to millions of degrees in its core, with a surface that boils and flings matter into space at hurricane speeds. And still, it gives us life. It shines exactly as much as needed. It warms but does not burn us. It does not go out, does not explode. How? What is the sun made of? The sun is not fire. It is a main sequence star, meaning a star in a stable phase of its life. Inside it, there is no flame. Nuclear reactions occur there. Approximately 75% of the sun's mass is hydrogen, about 24% is helium, and the rest is oxygen, carbon, neon, iron, and other elements. Its diameter is almost 1.4 million kilometers. That's more than 109 Earths lined up in a row. But even more incredible is its mass. The sun contains 99.86% of all the mass in the solar system. Everything else, planets, moons, asteroids, are mere fractions of a percent. We are circling a giant. How does the sun work? In the very center of the sun, in its core, the temperature reaches 15 million degrees. The pressure is so immense that hydrogen nuclei fuse to form helium. This is thermonuclear fusion, a process in which part of the mass is converted into energy. It is this conversion of mass to energy that is described by Einstein's formula E equals mc squared. Every second, the sun loses 4 million tons of matter, but it does not disappear, because it is enormous. The energy born in the core punches its way to the surface over hundreds of thousands of years, bouncing off particles like light and fog, and then, in just 8 minutes, it travels to Earth. And here it is, sunlight. It falls on your windowsill. It feeds leaves. It drives the weather. It reflects in your eyes. And all of this begins deep inside a star. The sun is not uniform. In the core, energy is born. Above it lies the radiative zone, where energy is transferred as light. Then the convective zone, where matter stirs like boiling soup. Above that is the photosphere, the surface we see. Its temperature is about 5,500 degrees, almost white, but it appears yellow to us because of the atmosphere. Higher up is the chromosphere, a thin layer. And finally, the corona, the sun's outer atmosphere, visible during a total solar eclipse. The temperature there unexpectedly reaches up to 2 million degrees. Why it is hotter than the surface is still one of astrophysics' puzzles. The sun not only shines, it ejects particles, streams of plasma that rush off in all directions. This is called the solar wind. Sometimes flares occur, sudden bursts of energy and matter. If they reach Earth, they can cause auroras, disrupt satellites, and even bring down power grids. Fortunately, Earth is protected. We have a magnetic field that deflects most of these particles. We literally live inside a giant bubble of solar wind, the heliosphere. This is the boundary of the sun's influence, stretching roughly 120 to 150 astronomical units beyond Pluto's orbit. It was this frontier that the Voyager probes crossed. How much longer will the sun shine? Right now, the sun is in a stable phase. It has already lived about half of its life. It has around 5 billion years left in this stage. Then it will start to expand, turn into a red giant, engulf Mercury, possibly Venus, and even approach Earth's orbit. Afterwards, it will shed its outer layers, leaving a white dwarf, a tiny, dense, cooling remnant, the heart of a dead star. But that is still billions of years away. For now, the sun is stable. And every morning when it rises, it reminds us, life goes on. The sun is not just a source of light. It is the beginning of the story. It keeps the planets in orbit, nourishes sprouts, gives birth to days and seasons. It allows us to live, love, think. Without it, there would be no breath, no thought, no dream. And it is in its shadow on one of its orbits that we live. In the following chapters, we will travel to those who circle around it, the planets. Each of them is like a chapter in a book, each with its own climate, character, and history. We approach the first planet from the sun, the fastest, the closest, the most silent. This is Mercury, a planet easy to miss from Earth. It is too close to the sun, hiding in its glow. It is hard to see even through a telescope, and yet it is one of the oldest stones in the mosaic of our system. The outer shell or crust of Mercury is very thin, about 20 kilometers. Its surface is covered with craters formed by intense bombardment by asteroids and meteorites in the early years of the solar system. One of the most impressive craters is Caloris, more than 1,300 kilometers across. It is so huge that the impact that created it caused chaotic terrain on the opposite side of the planet. The study of Mercury began with the Mariner 10 mission in the 1970s. This spacecraft sent back the first detailed images of the surface and discovered the existence of a magnetic field. But the real revolution in our understanding of Mercury came from the Messenger mission, which entered orbit around the planet in the 2000s. It collected data on surface composition, measured the magnetic field, and revealed many geological features. Mercury is a window into the past of the solar system. Its surface has hardly changed for billions of years, preserving traces of the early processes of planet formation. Its unusual structure and motion give scientists keys to understanding gravitational interactions, the influence of stars on close-in planets, and the cooling of planetary cores. Next, an even more mysterious planet awaits us, Venus, where conditions are so harsh that it is rightly called a hellish world. Venus is the second planet from the Sun and Earth's closest neighbor, surprisingly similar to our planet in size and mass. It is often called Earth's sister. But the resemblance ends with the numbers. Venus is a true cosmic hell, where unbearable heat, acidic clouds, and atmospheric pressure capable of crushing any earthly spacecraft in minutes reign. Yet behind all this extremity lies a story that may tell us how Earth's fate could have unfolded if our planet's delicate balance had been disturbed. Venus truly resembles Earth in the numbers. Its diameter is about 12,000 kilometers, which is only 5% less than Earth's. The planet's mass is about 82% of Earth's, and its density and gravity are also similar. If you stood on its surface, you would weigh almost the same as on Earth. Venus orbits at about 0.72 astronomical units from the Sun, roughly 108 million kilometers. This is closer than Earth, but not enough to explain its incredibly high temperatures. The reason for its catastrophic conditions is its unique atmosphere. Venus's atmosphere is one of the most extreme in the solar system. It is composed of 96% carbon dioxide, with small amounts of nitrogen and traces of sulfur compounds. The upper layers are covered with thick clouds of sulfuric acid that do not let sunlight pass. Because of this, Venus appears so bright and shiny in the night sky. Its clouds reflect up to 70% of incoming solar radiation. But under these clouds, at the surface, a true nightmare unfolds. The atmospheric pressure on Venus is 92 times higher than on Earth. This is equivalent to the pressure you would experience at a depth of 1 kilometer underwater. If we tried to build a base there, it would be crushed instantly. The surface of Venus is the hottest of all the planets in the solar system, with temperatures reaching 470 degrees Celsius. That is hotter than Mercury, even though Venus is farther from the Sun. The main cause of such temperatures is a runaway greenhouse effect that completely transformed the planet's atmosphere and climate. At some point in the past, Venus likely had conditions more similar to Earth's. There may even have been liquid water on its surface. However, its proximity to the Sun played a key role in the planet's catastrophic transformation. Because of the high level of solar radiation, temperatures began to rise, water evaporated, and water vapor, a powerful greenhouse gas, amplified heat retention. At the same time, carbon dioxide released through intense volcanic activity accumulated in the atmosphere, increasing its density and intensifying the greenhouse effect. The unique atmosphere of Venus makes its thermal dynamics truly extraordinary. Nearly 100% of the heat that reaches the planet is trapped in its dense carbon dioxide envelope. The upper clouds reflect about 70% of the sunlight, but the 30% that penetrates downward is absorbed by the surface and can no longer escape back into space through the thick gas layer. This process turns Venus into a true heat trap. Temperature on Venus is almost uniform across the entire surface, with minimal difference between day and night, or between equator and poles. This is due to the high density of the atmosphere, which redistributes heat evenly around the planet. Even at night, when the sun does not shine on the surface, the temperature remains nearly the same as during the day. Beneath Venus's dense atmosphere lies a remarkable world. Its surface has been studied using radar, since optical methods see nothing through the clouds. Venus is a world of volcanoes. Its surface is almost entirely covered by lava plains formed by eruptions in the past. One of the highest points on the planet, Maxwell Montes, rises about 11 kilometers above the surface, higher than Mount Everest on Earth. But most of Venus's surface is flat, etched with strange geological structures such as coronas, enormous circular formations created by magmatic activity. These coronas are traces of powerful tectonic processes that took place billions of years ago. Interestingly, despite its volcanoes and lava, Venus shows no clear signs of plate tectonics like Earth. Instead, its crust seems to bend and crack under pressure from below, creating unique landscapes. At an altitude of about 60 kilometers above the surface, incredibly strong winds blow at speeds up to 360 kilometers per hour. This phenomenon is called superrotation. The atmosphere rotates around the planet much faster than the surface itself. Venus takes 243 Earth days to spin once on its axis. This is the slowest day of any planet. Yet a year on Venus is only 225 days long. So a day on Venus is longer than its year. Venus was one of the first planets to be studied by spacecraft. The Soviet Venera missions were the first to send probes to its surface. Landers such as Venera 7 transmitted data from the ground, but survived no more than about 30 minutes due to the intense heat and pressure. Later, the European Space Agency's Venus Express mission studied the planet's atmosphere and dynamics, including superwinds and cloud chemistry. Today, new missions are planned, such as Da Vinci, Plus, and Veritas from NASA, which will examine Venus's terrain and internal structure. They may help answer the question of whether Venus could have been habitable in the past. Our next stop will be our home planet, Earth. We will learn what makes it unique and why it remains the only known home for life. The main feature that sets Earth apart from other planets is liquid water. About 70% of our planet's surface is covered by oceans, seas, and rivers. Water is the basis of life, and its unique properties, such as high heat capacity and ability to dissolve substances, make it ideal for sustaining biological processes. But why does Earth have liquid water, while Venus and Mars do not? The secret lies in the planet's location. Earth is in the so-called habitable zone, the region around a star where temperatures allow water to exist in liquid form. If Earth were slightly closer to the Sun, it might have shared Venus's fate. If slightly farther, it might have become a cold desert like Mars. Equally important is the magnetosphere, the magnetic field that protects our planet from the solar wind and cosmic radiation. The magnetosphere is generated by the motion of Earth's liquid iron core and acts like an invisible shield. Without it, the solar wind could strip away the atmosphere, as appears to have happened on Mars. Let us recall what the solar wind is. It is a stream of charged particles constantly emitted by the sun. These particles flow out of its hot outer layer, the corona, and move at speeds up to 800 kilometers per second, spreading throughout the solar system. The solar wind interacts with planets, causing various phenomena. On Earth, for example, it produces the aurora and interacts with our magnetosphere, which protects us from its destructive force. Earth is a dynamic planet, and its surface is constantly changing due to plate tectonics. The crust is divided into several large and small plates that float on the semi-fluid mantle. These plates move, collide, diverge, and subduct under one another, creating mountains, ocean trenches, and earthquakes. Plate tectonics plays a key role in the cycling of substances on the planet. For example, carbon dioxide released by volcanoes helps maintain the greenhouse effect necessary to preserve warmth. Plate motion also renews the crust over time, which supports the planet's long-term stability. Volcanism is another important part of geological processes. Volcanoes, besides their destructive power, deliver new material to the surface. They emit gases such as carbon dioxide and water vapor, which influence climate and minerals that enrich soil. Earth's atmosphere is another unique feature. Its composition is ideal for sustaining life. The main components are nitrogen, about 78%, oxygen, about 21%, and small amounts of carbon dioxide, argon, and other gases. This balance is not accidental. It was shaped by billions of years of biological and geological processes. Oxygen appeared in the atmosphere thanks to ancient microbes that began producing it via photosynthesis. This process, known as the Great Oxygenation Event, occurred about 2.5 billion years ago and changed the planet's chemistry, making it suitable for complex life. Carbon dioxide, though it makes up only a small fraction of the atmosphere, plays a crucial role. It regulates the planet's temperature via the greenhouse effect, keeping Earth from freezing. This delicate balance makes our planet comfortable for life, but also vulnerable. Any serious changes in carbon dioxide levels can lead to climate catastrophes, as happened on Venus. Speaking of our planet, we cannot ignore its faithful companion, the Moon. The Moon is more than just a beautiful object in the night sky. It plays a vital role in Earth's stability and the development of life. The Moon's diameter is about 3,470 kilometers, making it the largest moon in proportion to its planet in the solar system. First, the Moon stabilizes Earth's axial tilt. Thanks to this, the tilt stays relatively constant, providing stable seasons and climate. Without the Moon, Earth's tilt could wobble much more, causing chaotic climate changes. Second, the Moon causes tides. These cyclical movements of water in oceans, seas, and bays not only shape coastal ecosystems, but also played an important role in evolution. Scientists believe tides may have helped life transition from sea to land by providing varying environments for adaptation. Third, in the early solar system, the Moon acted as a cosmic shield, taking many impacts from asteroids and meteorites. Without it, Earth's surface might be much more battered. By studying Earth, we not only understand its uniqueness, but also learn to see the fragility of our home. The next planet we will examine is Mars, our nearest neighbor, which can tell us about Earth's past and perhaps its future. Mars is a planet that has attracted humanity's attention since ancient times. Its reddish color in the night sky inspired myths and associations with war and destruction. But today, Mars symbolizes not war, but hope. For us, it has become a window into the past of the solar system and, perhaps, into humanity's future. Let us understand why Mars fascinates us so much. Mars is the fourth planet from the Sun at an average distance of 228 million kilometers, or about 1.52 astronomical units. That makes it almost 1.5 times farther from the Sun than Earth. As a result, Mars receives much less heat and sunlight. In size, Mars is about half of Earth, and its surface area is comparable to the total land area of our planet. Mars's mass is only 11% of Earth's, and gravity at its surface is about 38% of Earth's. This means that if you weigh 70 kilograms on Earth, you would weigh only 26 kilograms on Mars. Mars is a frozen desert. Its average temperature is about -63 degrees Celsius, but depending on season and location, it can range from -125 degrees Celsius at the poles in winter to +20 degrees Celsius at the equator in summer. These sharp fluctuations are due to the thin atmosphere, which barely retains heat. Mars's atmosphere is so rarefied that its pressure is only about 0.6% of Earth's, similar to conditions 30 kilometers above Earth's surface, 3 times higher than commercial airplanes fly. It consists of 96% carbon dioxide, with small amounts of nitrogen, argon, and traces of oxygen and water. One of Mars's most striking features is its dust storms, which can engulf the entire planet. These storms lift fine dust high into the atmosphere, dimming sunlight and making Mars even colder. The largest recorded storm, in 2018, lasted several months and led to the end of the Opportunity rover's mission. Yet the surface of Mars is astonishing. Red wastelands of oxidized iron, enormous volcanoes, ancient dried riverbeds, and ice caps at the poles all tell the story of a planet that may once have been very different. Imagine Olympus Mons, the tallest volcano in the solar system, 22 kilometers high. That is 3 times taller than Everest, and its base is so vast you wouldn't see the summit from the foot. Or the Valles Marineris Canyon System, a network of valleys 4,000 kilometers long and up to 7 kilometers deep, 10 times longer than the Grand Canyon, and 4 times deeper. Scientists believe these structures were formed by tectonic processes and possibly flowing water. Yes, water is the key to Mars's mystery. Today, there is no liquid water on its surface, but we see traces of its presence everywhere. Billions of years ago, Mars was warmer. With a denser atmosphere, rivers flowed here, lakes formed, and perhaps even an ocean covered a significant portion of the planet. Now water on Mars exists only in the form of ice, in polar caps or underground. There is also speculation that under the frozen soil, especially in the South Polar region, subsurface lakes of liquid water may exist. These findings give hope that life may have existed on Mars in the past and may even still be hiding there today. Currently, Mars is the main target of planetary exploration. Rovers like Curiosity and Perseverance continue to study its surface, collecting data on climate, soil composition, and traces of ancient life. Curiosity, operating since 2012, has confirmed that Mars once had conditions suitable for life. Perseverance, which arrived in 2020, is exploring Jezero Crater, the site of an ancient lake and river delta where microbial life could have thrived. But our ambitions do not end there. Elon Musk, with SpaceX, dreams of sending humans to Mars as early as the 2030s to begin building the first settlements there. Our next stop will be Jupiter, the king of planets, which will show us a completely different cosmic world. Our journey through the solar system continues, and now we leave the realm of rocky planets, heading to where giants rule. Between Mars and Jupiter stretches the asteroid belt, a region filled with millions of rocky and metallic objects that never managed to merge into a full-fledged planet. Scientists believe Jupiter's immense gravity prevented that. The first to greet us is Jupiter, the most massive and enigmatic planet in the solar system. It is so large that more than 1,300 Earths could fit inside it. Its influence extends far beyond its orbit. This gas colossus not only governs the motions of its moons, but also acts as a kind of cosmic shield, drawing in asteroids and comets that might otherwise threaten Earth. Jupiter is a world of storms, crushing hurricanes, incredible pressure, and magnetism that extends millions of kilometers into space. It is impossible to imagine it without its eternal great red spot, its spectacular auroras, and its 4 largest moons, each nearly a world in its own right. Jupiter's mass is more than 318 times that of Earth, but if it grew further, it would not get much bigger in size. Beyond a certain point, gravity would compress it instead of allowing it to expand, making it denser rather than larger. Its gravity is 2.5 times stronger than Earth's. If a person could somehow stand on Jupiter's surface, they would weigh 2.5 times more, though in reality, there is no solid surface to stand on. Jupiter is composed mostly of hydrogen and helium, much like the Sun. If you descended below the outer clouds, you would pass through layers of increasingly dense gas. First comes the atmosphere filled with whirling ammonia and methane clouds, with storms stretching thousands of kilometers. Deeper down, the pressure increases so much that hydrogen becomes liquid and then metallic, turning into a substance we can create on Earth only in laboratories at extreme pressures. This ocean of metallic hydrogen, tens of thousands of kilometers deep, behaves like a metal and conducts electricity. It is here that Jupiter's incredibly powerful magnetic field is generated, extending millions of kilometers around the planet. What lies deeper still? Possibly a small rocky core about the size of 10 Earths, but scientists are still debating this. It is quite possible that under the immense pressure, this core has partially dissolved into the surrounding hydrogen. Jupiter would not be Jupiter without its turbulent banded atmosphere. These bright and dark stripes are the result of powerful winds blowing in opposite directions at up to 600 kilometers per hour. The entire atmosphere is a boiling ocean of gas, where constant vortices create intricate patterns. Lightning flashes that are thousands of times brighter than on Earth, and in the lower layers the pressure compresses gas into a liquid state. And of course, we cannot forget the Great Red Spot. This giant storm is a true veteran among hurricanes, raging for at least 350 years. Today, its diameter is about 16,000 kilometers, several times larger than Earth, and this is already smaller than it used to be. The spot is gradually shrinking. Scientists do not yet know whether it will eventually disappear entirely, but for now, this storm remains one of the most impressive phenomena in the solar system. Jupiter's magnetic field is the strongest among all the planets, about 20,000 times stronger than Earth's. It creates a gigantic magnetosphere that, if visible, would cover more sky than the Moon. Jupiter is a true radiation hell. Streams of charged particles rage around it, and the radiation levels are deadly, even for heavily shielded spacecraft. That is why missions like Juno have to perform complex maneuvers to avoid the most dangerous regions. Jupiter is not just the planet itself, but also its moon system. It has more than 80 moons, but the most famous are the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. Each is a distinct world with its own history and unique features. Io is a volcanic hell, the most geologically active body in the solar system. Volcanoes on Io constantly shoot lava tens of kilometers high, and its surface is covered with sulfur, giving it a bright yellow hue. Its interior is heated by powerful tidal forces from Jupiter and the other moons. Europa is a world beneath the ice. Its surface is a crust of ice several kilometers thick, but beneath it lies an ocean of liquid water, and not just an ocean. Its volume may exceed that of all Earth's oceans combined. The surface is crossed by cracks from Jupiter's tidal forces, and geysers have been observed that eject water into space. If there is life anywhere in the solar system apart from Earth, Europa is one of the main candidates. No less fascinating is Ganymede, the king of moons. It is larger than the planet Mercury and is the only moon in the solar system known to have its own magnetic field. Its surface is covered in ice and ancient craters, and under the surface there may also be a subsurface ocean. Callisto is an ancient, heavily cratered world, one of the oldest objects in the solar system. Its surface has changed very little over billions of years. Like Ganymede, it may hide an internal ocean beneath its icy crust. Jupiter was the first planet to be studied up close. In the 1970s, Pioneer and Voyager flew past it, but the most detailed investigations were carried out by the Galileo mission in the 1990s and the current Juno mission. Future studies of Jupiter promise to be even more exciting. In the 2030s, the JUICE mission will head to Ganymede, and the Europa Clipper mission will investigate Europa's icy surface and try to determine whether life could exist in its ocean. Jupiter is undoubtedly the king of planets, but its neighbor Saturn is no less astonishing. It is a world that seems to embody alien beauty, surrounded by the grandest ring system in the solar system and possessing Titan, a moon where rain made of liquid methane falls. It's time to move on and find out what this mysterious planet hides. After Jupiter, our path leads farther, toward Saturn, a planet that is truly one of the most beautiful in the solar system. If Jupiter can be called the king by size and power, Saturn is his aristocratic brother, surrounded by the most stunning ring system, making it utterly unique. Saturn is the second largest planet in the solar system. Its diameter is about 120,000 kilometers, roughly 9.5 times Earth's. Yet despite its enormous size, Saturn is the least dense planet of all. Its average density is lower than that of water. This means that if there were a sufficiently large ocean, Saturn could float in it. But of course, its main feature is its magnificent rings, which have made it one of the most recognizable planets in the solar system. When we look at photographs of Saturn, the rings appear solid and continuous, like a flat disk. But this is an optical illusion. In reality, they consist of billions of particles of ice and rock orbiting the planet. Their size ranges from tiny grains of dust to boulders the size of a house. The thickness of the rings is incredibly small compared with their width, only about 10 meters on average, while their diameter exceeds 200,000 kilometers. In essence, they form a giant, thin disk so slender that from the side it practically disappears. Scientists still debate the rings' origin. One hypothesis suggests they are remnants of a destroyed moon that came too close to Saturn and was torn apart by its gravity. Another is that this is material which never formed a moon due to Saturn's own gravitational influence. Within the rings are interesting features, such as the Cassini division, a huge gap about 4,800 kilometers wide, separating the rings into two main parts. The culprit behind this gap is Saturn's moon Mimas, whose gravitational resonance sweeps particles out of this region. Like Jupiter, Saturn's atmosphere is mostly hydrogen and helium, with traces of other gases that give its clouds yellowish and golden tones. But while Jupiter's most famous atmospheric feature is its great red spot, Saturn has an equally mysterious structure, a hexagonal storm at the North Pole. This structure is a true scientific phenomenon. Imagine a giant cyclone 25,000 kilometers wide, shaped like a perfect hexagon. Inside swirl winds over 500 kilometers per hour, while the edges remain remarkably sharp, as if drawn with a ruler. Scientists still do not fully understand why the storm has this shape. Saturn has other atmospheric surprises. In 2010, the planet's northern hemisphere unexpectedly changed color from bluish to golden. This transformation was caused by photochemical reactions from sunlight. When summer arrived in that region, ultraviolet radiation broke down molecules responsible for the bluish tint, and clouds took on warmer hues. But Saturn is not just the planet itself. It has 83 moons, among which Titan stands out. Titan is one of the most intriguing objects in the solar system. It is the second largest moon after Ganymede, larger than Mercury, and the only moon with a dense atmosphere. And that atmosphere makes it truly special. If you stood on Titan's surface, the sky above you would be orange-yellow. Around you would stretch plains covered with frozen hydrocarbons. The strangest thing is that it rains there, not water, but liquid methane and ethane. At a temperature around minus 180 degrees Celsius, water is as hard as rock, while rivers, lakes, and seas are made of hydrocarbons that remain liquid. This world strongly resembles Earth in some ways. It has seasons, clouds, and precipitation. Rivers and lakes change with the seasons. We observe how some methane seas slowly evaporate, while new bodies of liquid form elsewhere. Deep beneath Titan's surface, there may be a subsurface ocean of liquid water. If so, it may offer conditions suitable for life. If Titan draws attention with its dense atmosphere, another of Saturn's moons, Enceladus, amazes with its geysers. Enceladus is tiny, only about 500 kilometers in diameter, yet incredibly active. The Cassini spacecraft discovered that jets of water shoot from its south pole into space, forming vast plumes. These geysers are so powerful that the ejected ice particles form one of Saturn's rings. Beneath Enceladus's surface lies an ocean of liquid water. In its composition, scientists have found organic molecules and signs of chemical reactions that could provide energy for life. This makes Enceladus, along with Europa, one of the top candidates in the search for extraterrestrial life in the solar system. The most detailed study of Saturn and its moons came from the Cassini-Huygens mission. Launched in the 1990s, Cassini spent 13 years in the Saturn system, sending back thousands of images and unique scientific data. The Huygens probe, which separated from Cassini, landed on Titan, the first landing on the surface of a moon of another planet. It transmitted pictures of the orange haze, rocky plains, and signs of ancient riverbeds. In 2017, Cassini completed its mission by diving into Saturn's atmosphere, sending data to the final moment. Saturn is the last of the gas giants, but beyond it lie Uranus and Neptune, icy worlds hiding no fewer secrets. They have incredibly strong winds, strange magnetic fields, and moons that may conceal subsurface oceans. After traveling through Saturn's realm, we journey further into the depths of the solar system, into the world of the ice giants. Uranus is the seventh planet from the Sun. Although it is smaller than Jupiter and Saturn, it impresses with its uniqueness. It seems to break all the rules. Blue, mysterious, rotating on its side, surrounded by rings and moons with astonishing terrain. Its cold, harsh atmosphere hides secrets that remain poorly understood. Like Jupiter and Saturn, Uranus is a giant, but it belongs to a different class. While the two largest planets mainly consist of hydrogen and helium, Uranus and Neptune are categorized as ice giants. What does this mean? In Uranus, a much larger proportion of heavier substances, such as water, ammonia, and methane, is present. Instead of a deep layer of metallic hydrogen like Jupiter's, Uranus's interior likely contains a vast icy mantle of these compounds. If you could descend into Uranus's atmosphere, you would first pass through its upper clouds, primarily methane and hydrogen. Then the pressure would increase, gradually compressing gases into liquids and ices. If you ask whether there is a solid surface to stand on, the answer is no. The atmosphere gradually transitions into deeper layers, and the closest thing to a surface is the level where pressure is similar to Earth's sea level. At the center, there is probably a rocky core about the size of Earth, wrapped in a thick layer of hot, icy mantle. The temperature inside may reach 5,000 degrees Celsius, but the dense icy layer prevents this heat from escaping efficiently. This is one reason Uranus is among the coldest planets in the solar system. Its average temperature is around minus 224 degrees Celsius, making it colder than even more distant Neptune. Why? Uranus emits very little internal heat compared to other giants. The most striking feature of Uranus is its bizarre axial tilt. Unlike other planets that rotate more or less upright, Uranus is tilted by about 98 degrees. It essentially rolls around the sun on its side. Its poles alternately face the sun and then sink into long darkness. This makes Uranus's seasons the most extreme in the solar system. While on Earth, winter and summer change every 6 months, on Uranus one pole faces the sun for 42 years, then spends another 42 years in night. Why? Scientists believe that in its early history, Uranus suffered a collision with a huge object, possibly a planet the size of Earth. That impact tipped it over. Although Uranus appears as a calm blue sphere, its atmosphere is highly dynamic. It consists mainly of hydrogen, helium, and about 2% methane gives Uranus its blue color by absorbing red light and reflecting blue and green. Winds on Uranus can blow at up to 900 kilometers per hour, faster than the strongest hurricanes on Earth. Sometimes giant storms appear in the atmosphere, but they are difficult to observe through the dense clouds. Though rings are often associated with Saturn, Uranus also has them. They are much thinner and darker, composed of material that reflects little light. But the real wonders lie among its 27 known moons. The most unusual is Miranda. This moon looks as if it were assembled from fragments. Its surface is carved by giant faults, cliffs, and chasms. Some of its canyons are deeper than Earth's Grand Canyon. Scientists think Miranda may have been shattered by a powerful impact, then reassembled from its own fragments, giving it its chaotic appearance. So far, only one spacecraft has ever visited Uranus, Voyager 2, which flew by in 1986 and sent the first and only close-up images. Since then, no missions have returned, but scientists are planning a new exploration. Perhaps in the 2030s, NASA will send a probe to study Uranus's atmosphere, moons, and internal structure in detail. After the icy and mysterious Uranus, our journey reaches the last of the known giants, Neptune. The most distant, the most wind-swept, and perhaps the most mysterious. At first glance, Neptune looks similar to Uranus, a bluish sphere cloaked in clouds. But upon closer inspection, the differences show. If Uranus is a quiet, cold world, Neptune is a violent, stormy giant with the strongest winds in the solar system. This is the master of cosmic winds, and its story is full of puzzles. Neptune is an ice giant like Uranus, but with a more active, dynamic atmosphere, Made mostly of hydrogen, helium, and methane, it has a deep blue color, similar to Uranus, but its defining feature is its winds. In Neptune's atmosphere, the winds are the strongest anywhere in the solar system. Their speed can reach 2,400 kilometers per hour, faster than the speed of sound in Earth's air, and 3 times the speed of the most destructive terrestrial hurricanes. Scientists still do not fully understand how Neptune maintains such violent weather. It receives only about 1/9 the sunlight that Jupiter gets, and its upper atmosphere seems cold and calm. But deeper layers are a true inferno of storms and vortices moving at tremendous speed. Neptune also has its own giant storm, the Great Dark Spot. When Voyager 2 first imaged Neptune in 1989, scientists saw a huge dark region similar to Jupiter's Great Red Spot. It stretched about 8,000 kilometers across, with winds inside reaching 2,000 kilometers per hour. But when astronomers later observed Neptune with the Hubble telescope, the dark spot had disappeared. It simply dissipated. Later, new dark spots, new giant storms, were seen forming and vanishing every 5 to 10 years. Neptune is the only planet where such massive storms appear and disappear on timescales of decades rather than centuries. Like Uranus, Neptune has no solid surface. Any attempt to land would result in sinking deeper into dense gas under ever-increasing pressure until it crushes anything that descends. Compared with the gas giants, Neptune contains more ices and heavy compounds like water, ammonia, and methane. Beneath its thick atmosphere lies a deep icy mantle of these materials. Beneath that is a hot, dense core of rock and metal, where temperatures may reach 7,000 degrees Celsius. Neptune emits about twice as much heat as it receives from the sun. This internal energy is likely what powers its storms and winds. Among Neptune's 14 known moons, Triton stands apart. It is the largest and one of the strangest objects in the solar system. Triton's main oddity is that it orbits Neptune in the wrong direction, retrograde, opposite the planet's rotation. Most moons orbit in the same direction their planets spin, but Triton moves the other way. This means it likely did not form around Neptune, but was captured from the Kuiper belt. Its surface is covered with nitrogen ice, and its temperature is around -235 degrees Celsius, making it among the coldest places in the solar system. Yet, the most surprising feature is its icy geysers. Voyager 2 observed jets of nitrogen erupting from the surface, indicating an internal heat source capable of warming ice and causing it to evaporate. Some scientists suspect a subsurface ocean of liquid water beneath Triton's frozen shell, similar to Europa or Enceladus. To date, Voyager 2 is the only spacecraft ever to visit Neptune. No new missions have gone there since. But in recent years, astronomers have been discussing new projects. One concept is Neptune Odyssey, an orbiter that could study the planet in detail. NASA is also considering the Trident mission to Triton, which would test the subsurface ocean hypothesis, but such missions would take decades. Even if launched soon, a probe would not reach Neptune until the 2040s. Our journey through the solar system's planets has ended, but the system itself does not. Beyond Neptune stretches the Kuiper belt, where thousands of icy worlds dwell: Pluto, Haumea, Makemake, and other dwarf planets. We have covered all 8 planets, but between them and beyond lies a vast population of small bodies, asteroids, comets, dwarf planets, and meteoroids. These objects may seem insignificant compared to giants like Jupiter or Saturn, but their role in the system's formation and evolution is immense. They preserve information about its distant past. Some even pose potential threats to Earth. When astronomers first began systematically surveying the sky, they expected to find another planet between Mars and Jupiter. From orbital patterns, it seemed another world should be there. Instead of one planet, they found an asteroid belt, a region filled with millions of small objects that never formed a full planet due to Jupiter's gravity. Asteroids vary widely in size, from giants like Vesta, about 525 kilometers in diameter, to tiny rocks just a few meters across. They consist of metals, silicates, carbon-rich compounds, and some even contain water. Besides scientific value, asteroids pose a real danger. About 66 million years ago, one such object struck Earth, causing the extinction of the dinosaurs today. Astronomers closely monitor potentially hazardous asteroids that might cross Earth's orbit. The largest known ones are currently safe, but smaller objects can still pose a threat. For this reason, NASA and other agencies are developing planetary defense methods, including missions like DART, which successfully altered a small asteroid's orbit in 2022. For a long time, Pluto was considered the ninth planet. In 2006, however, astronomers redefined the criteria and reclassified Pluto as a dwarf planet. This caused intense debate. For many, Pluto remained a real planet. Why was it demoted? The reason is that Pluto does not dominate its orbit. Around it lie other bodies, Haumea, Makemake, Eris, that might also claim planetary status. All are in the Kuiper Belt, an enormous region beyond Neptune filled with icy objects. Despite its new status, Pluto remains a fascinating world. It has 5 moons, the largest of which, Charon, is so big relative to Pluto that the pair form a dual system, orbiting a common center of mass. Pluto's surface is covered with icy plains and cryovolcanoes, volcanoes that erupt liquid nitrogen and methane instead of lava. Its atmosphere is made of nitrogen, methane, and carbon monoxide, forming a bluish haze similar to Earth's sky. When the New Horizons spacecraft flew past Pluto in 2015, it sent back images that astonished scientists. This small world turned out to be far more complex and active than expected. Asteroids are mostly rock and metal, while comets are dirty snowballs, mixtures of rock, ice, frozen gases, and organic molecules. When a comet approaches the sun, it begins to heat up and sublimate, forming a tail. This tail always points away from the sun, shaped by the solar wind sweeping out the escaping gases and dust. Comets come from 2 main reservoirs. The Kuiper Belt close to us is the source of short-period comets like Halley's Comet, which returns every 76 years. The distant Oort cloud is a gigantic spherical region at the edge of the solar system, from which long-period comets like Hale-Bopp arrive. Comets likely played a key role in Earth's history. Some scientists believe they delivered much of our water and perhaps the organic molecules necessary for life. And what about meteorites? These are small fragments of asteroids or comets that fall to Earth. Most burn up in the atmosphere, creating the beautiful effect of shooting stars. But some reach the surface. The most famous in recent times is the Chelyabinsk meteor of 2013, whose airburst shock wave shattered thousands of windows. Today, we have traveled from the blazing heart of the sun to the icy frontiers of the heliosphere. We passed over Mercury's craters, through Venus's clouds, looked back at Earth from light minutes away, glimpsed Mars, flew by Jupiter's storms, Saturn's rings, Uranus's tilted horizons, and distant blue Neptune. We crossed paths with comets, asteroid belts, and the lonely orbit of Pluto. Looking back, we see these are not just planets. This is the history of matter. These are our roots. Once, everything we saw was dust, and that dust became stars, planets, and us. We are children of the sun. We carry in our bones calcium forged in the cores of stars. We breathe oxygen squeezed out by ancient solar-powered processes. We think with a brain built of carbon formed billions of years ago in other galaxies. Space is not somewhere out there. It is within us. And as you close your eyes, imagine, outside your window, it is night. But this is not just darkness. It is the universe. Perhaps at this very moment, on the other side of the galaxy, someone is looking at the sun as a distant star. Perhaps someone dreams of touching Saturn's rings, just as we dream of touching the stars of Andromeda. Perhaps everything repeats, or perhaps it is only just beginning. And if tomorrow you happen to look at the sky, maybe you will already know where your home is. Among all those distant stars, among all those impossible distances, there is a point where a soft, steady light burns. It is called the sun, and circling it is Earth, and on it, you. Thank you for spending this night with us. May you dream of the sky, and may you, in your sleep, once again fly through the solar system, slowly, freely, peacefully, until we meet again in our nightly wanderings